Welcome all.
Thank you, Arif.
And Professor Luis and Vitor knows me, but everyone not knows me. So, Mariana, I'm very happy to hear you.
Sorry, I don't understand very well.
Okay, can you hear me correctly?
Yes.
Okay, thank you so much. I'm very happy to be here with you. This is my very big pleasure. So, I'm semi-Portuguese citizen, as you know. That's the reason I'm so happy to be here again. Maybe next time we will meet as the same place. This is my pleasure, as you know, because Portugal is my second country. That's the reason I'm so happy to meet you with our Imascon Congress.
Thank you, Arif.
Thank you so much.
Thank you, Arif.
Okay, Professor. If Professor Rosario here, so the microphone is you.
Okay. Thank you, Professor Arif. Thank you, everybody. Thank you, Shatai, and all that are here. It's a pleasure for me and for us. Vitor also included to be here in Imascon is a reference also for us. So it's a pleasure to collaborate. We have invited several researchers making PhD that are preparing the final part of work, some of them, not all, but some of them. So the idea of this year for biomedical talks is to have 5 different talks in sport biomechanics, in orthopedic biomechanics, and try to share what they are doing and make some discussion if we have a little of time. I see that you have a class in the meeting. Hello, everybody. It's very nice to have you in the meeting. We also invite students from Biomedical and 2 French students from University of Paris, of Nanterre. They are also attending the meeting. And for the beginning, I think it's enough. I don't know, Arif, if you want to talk something else, or Shatai?
Thank you so much. If you want, we will start. Who is the first?
The first one will be Catarina Amaro. And the title... Catarina. And the title of the work is Impact of Sex Differences and Upper Limb Strength on Ball Release Kinematics in Basketball Shooting. It's your domain, Arif. Basketball.
Don't forget, after this session, you will enter Imascon internet site and register our Congress and upload your abstracts, okay? Imagine that last time, as you know. Thank you so much. Okay, Katarina. We are listening to you. Thank you so much.
Okay, I will share.
8 to 10 minutes, please.
Okay.
Okay. I'm trying to share my...
Is it problem
video.
to sharing process? Okay, I will control this one. Pardon me. Wait me in minute. Okay. Pardon me. Okay. No problem. is the problem for sharing process. Wait me a minute. That's enough. I will control again. That's okay, Katarina. If you want, you will
Yeah.
share.
I'm trying to.
Okay.
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 You can
I will
see?
see. Yes, I will see your presentation. Thank you so much.
Okay. So, hello everyone. As Professor Luis told you, I'm Catarina and I'm from the University of Coimbra. And today I'll present a part of my PhD project and I will talk about how sex differences and upper limb strength affect the ball release in basketball shooting. Okay. In basketball, performance is influenced by many factors: physical, technical, tactical, and physiological. My focus on this project or on this part of my project is on technical part, especially the moment the ball is released during the shots. We know that men and women, or we think that men and women shoot differently, and strength may explain some of these differences or not. We'll see that during my work and during this presentation. In this study, we had two goals. The first is to compare the ball release height, angle, and velocity between male and female players. And the second one is to see if the grip strength measured with a dynamometer is related to these variables, and if the relations changes by gender, by female and male. For this, we use the sample with the 5 males and 7 females. All of them played in the seniors team that compete in the national championship and with at least 7 years of federated practice. Players performed 90 shots, 10 shots in each position and condition, all of them from 3 points line, but we changed the angles and we measured the kinematic with a quality system, recording at a frequency of 200 Hertz. Before the acquisitions, we did the anthropometric measurements, which includes the dynamometer, and we did 3 repetitions, and we considered only the maximum value of the dominant hand, not from both, but only the hand that shoots the ball. Wait. From that analysis, we use the statistical parametric SPSS, and to compare males and females, we use the Med-Whitney-U test because our data was not normally distributed. And after that, we run Pearson correlations between grip strength and each kinematic variables separately from men and women. Now let's look at the differences between male and females. The first graph, we can see the normalized release heights. And as you can see, male players release the ball higher even after adjusting for their body heights, which means that we divided the release height from the athlete heights, and we had values from like 0.9 and 1.30 or something like that, because if we only use the release heights, males will shoot the ball higher than females, like in every shots, because our sample had higher males than females. In the second graph, we can see the release angle, and here we saw that female players had higher angles than males, and this also showed a significant difference between both. And in the last one that is related to release velocity, we can see that the difference is not statistical significant, but we can see a tendency to the male players shoot with lower velocity than the women's. After that, we did the correlation with the grip strength, and we can see that we only have two correlations that have significant values, both of them in the male ones. So in the left, we see the male variables, in the right, we see the woman ones. And in female players, we have no significant correlations. And in male ones, we have two moderated ones, both of them with positive correlations, which means that with higher grip strength, the athletes shoot higher and with a higher velocity too. This means that stronger players, for male ones, shoot from a better position and with more velocity, and for female players, the strength didn't seem to affect the shooting mechanisms. To conclude, male players shoot higher and with lower angles. Grip strength influences shooting only in males, especially for release height and speed, and females may use more technical or coordinated strategies. And probably female players shoot with a higher arc. We didn't measure that in this study, but consider the angle, we can think that they should be the higher arc. To finish, I would like to thank my supervisors and to thank you all for listening. And I'm happy to answer your questions if you have some.
Thank you so much for your valuable presentation. It's very interesting topic so much. And I hope you will end your process PhD or another things also. So thank you so much.
Thank you.
Arif,
Yes, sir.
can I put a question to Katarina? Or you think it's better to have the questions at the end for all?
Yes, maybe it's at the end. I have some questions for all of your presentation. And also, Çağatay, is there any question for you?
Okay. So
Okay.
at the end we will discuss.
Okay, discuss. Okay, sir.
Good. So let's continue. And now we have Mariana Santos with the work Rebuilding Alignment, Surgical Strategies, Support Devices, and the Future of Tibial Osteotomy, a review.
It's very interesting topic. So, Mariana, are you in the laboratory now?
No, not today.
Not today, okay.
Okay. You are seeing my screen?
Yes. Tibial alignment osteotomy, surgical techniques, assistive devices, and current technologies, JABS.
It's not the correct part, Mariana. It's the correct monitor.
Let me see. I can show you the presentation view. Maybe this way? No?
Yeah.
Yeah, better.
Good.
Yeah.
Okay.
Okay. So, hello, my name is Mariana Santos. I'm a PhD student at the University of Coimbra. Today I'm going to talk about tibial alignment osteotomy. What is it, how it's done, and how the technology is helping to make the procedure better and safer. This kind of surgery is very important for younger people with knee problems who are not yet ready for a full knee replacement. When the knee is not well aligned, one part of it can wear down faster than the other one, especially in the case of osteoarthritis. Tibial osteotomy helps by changing the way the weights go through the knee. Instead of replacing the joint, we adjust the angle of the leg bone to take pressure of the damaged part. This can improve movement, reduce pain, and make the joint last longer. But for the surgery to work well, the alignment needs to be very precise, and that's where planning and technology comes in. There are too many techniques used. The first is called medial opening wedge. In this one, the surgeon makes a cut in the tibia and opens a small gap to release the leg. The gap is then filled with bone grafts or a spacer and help with the plate. This method keeps the bone mostly in place and allows small correction. The second is lateral closing edge. In this case, a wedge of the bone is removed from the outside of the tibia and the two edges are bolted together. This gives a strong correction, but it shortened the leg slightly. Each method has advantage and disadvantage, and the best choice depends on the patient's anatomy, the goals of the procedure, and the surgeon experience. The table on these slides shows a comparison of both techniques. To help the surgeon be more precise, several assistant tools can be used. Plates like StomoFix are attached to the bone to keep everything stable while it heals. There are also patient-specific cutting guides, and we have also using 3D image of the patient's leg and show the exact spot of the angles for the bone to cut. This makes the surgery faster and more accurate. Some hospitals use computer systems during the surgery to guide the surgeon in real time, but these systems show how much the bone has moved and whether the alignment is correct or not. Planning softwares are also let the doctor simulate the surgery ahead of time, which helps improve results and avoid surprises. Even with all these tools, there are still some issues. One of the big problems is that the systems used to plan the surgery doesn't allow it connected well with the tools used during the procedure by itself. Another problem is that not all of the patients are the same, and some devices doesn't adapt well to different body shapes. There are also a lack of standard ways to do the surgery. Surgeons may use different techniques in different places. We also don't have enough studies comparing the long-term results of these methods. And finally, in some hospitals or countries, the advanced tools are not available for the major of the surgeons, and they are too expensive. To solve these problems, new technologies are being developed. For example, 3D printing lets doctors make cuttings, guides, and even implants that fit the patient perfectly. Artificial intelligence could help by learnings from past surgeons and suggesting better ways to plan. Augmented reality may let surgeons see guides or plans over the patient's leg during the surgery, which can help improving the accuracy. Biomechanical models can predict how the leg will work after surgery, which helps plan recovery. To summarize it, a tibial osteotomy is a great option for people with knee problems who want to avoid the full replacement. The technology is improving results, but there is still a need for better integration, easy access to the tools, and more research to support decisions making. And this is where our work makes sense and aims to help innovation, creating a system that assists and simplifies the surgical procedure. I would like to thank my professor and my teams for the support and the guide. This research was supported by public funding from the Research Center. Thank you all very much, and I will be happy to answer any questions.
Thank you so much. At the end, I have some questions at the end of this session. And also, my Portuguese is not good, so I have some words. Esto esperando você kunne próxima nas. Maybe next time we will meet here, okay?
Okay.
This is my bad Portuguese so much.
No, very good.
Very good.
Very well, yes. Okay. Thank you, Mariana. You can stop sharing. Okay. Thanks. So the questions will be at the end. And now we move to our Vitor Maranha. The work presented by Vitor Maranha is shoulder joint biomechanical model parameterization. Why?
Okay, let's see if I can share. Okay. Is it in the correct mode?
Yes.
Yes.
Okay, thank you. So my presentation today will talk about the shoulder joint, which is my research theme at the moment, by my PhD theme, and I will speak about the biomechanical model parameterization and why is that. The question is simple because as we start to study some kind of joints, even the shoulder joint, we have two different biomechanical models, and with different biomechanical models, we achieve different results, and that's the question that cannot be answered at the moment. So we should have the same models to have the same results. By that, I'm going to talk about something about the shoulder anatomy, the anatomical and orthostatic position, which is a starting point of our shoulder position. Then about the typical source of our shoulder models, typical analysis, and the new approach that I'm going to propose today, and some conclusions about this comparison between the older or the traditional approach or the new approach. So as you know, we all know, the shoulder joint is in the upper limb of the human body. It has an important group of muscles that promote stability and some kind of movement, supraspinatus, infraspinatus, subscapularis, and teres minor. Then it has some stability and cushioning elements like ligaments and bursas that promote almost the stability of the shoulder joint. And my focus of my research at the moment, which are the shoulder joints, composed by four different bone structures. The glenohumeral joint, which is used in almost all the research. The only focus is this only joint, the glenohumeral joint, the chromicoclavicular joint, and the other one, which most of the studies does not comprehend, which is the sternoclavicular joint. So, as we all know, the shoulder has four different bone structures: the sternum, which is in the center of the human body, the upper limb. Then, side by side, we have the clavicle, the scapula, and the humerus. By that, we can have three different shoulder joints, which are important for our studies. As I said before, glenohumeral joint, chromicoclavicular joint, and sternoclavicular joint. But when we have these kind of models to make our research, we don't know which are the relative position between these structures. So we can find different positions, humerus and scapula different positions. So we don't have a common starting point. So we cannot achieve the same results. Even if by the top view, lateral view, we don't know the relation between these elements. Why is that? Because typically we get these models from CT scans, And as we can see, these different examples, we can conclude that the relation between the elements are different. If we get a CT scan by a patient in the supine position, is different the relative position of the bones when the patient is standing position. By that, we will get different models, different analysis, and different results. Then we can also get some joint or shoulder joint models by MRI, and also depends on the patient, the position, and also of the segmentation that we promote to get the physical models. And the other one, of course, when we get the models by dynamic inverse kinematic analysis, we can see that we get different alignments of the complex shoulder. So with different models or base models, the analysis will also be different. Rather will be finite element analysis, different positions, different results, or even if we have to make a multi-body analysis, if the starting point is different, of course, the final results will also be different. So what I propose here is a starting point position so that every different analysis that the researchers do have the same conditions and the same results. So we acquire a sawbones CAD model, digital model, the sternum model, the clavicle model, the scapula digital model, and also a humerus model. And we started our assembly using the SolidWorks. As a starting point, we use all the same and common anatomical and axis planes. We did it in SolidWorks, the same anatomical and planes and axes to have a correct reference of anatomical positions. Then we started to place the sternum, and by the literature review and using the International Society of Biomechanics, we placed the sternum in the correct position. As we know, the sternum is a fixed geometry in the human body, not so fixed, but we assumed as a fixed position, and everything will work around the sternum. So the following step was to get the correct landmarks, planes, and axes of the clavicle. Then we place it in the correct place, once again based on the important literature review. The following step was to place correctly the scapula, which, as we see in detail, is 60 degrees with the retroversion compared with the center anatomical plane. And by the end, we placed the humerus with also a retroversion with an anatomical position. Once again, I have to refer that these positions, these references, this parameterization was based on the International Society of Biomechanical recommendation and also in a very important review. So this is the correct starting point for any analysis that we can promote, even if it is a finite element analysis, multi-body biomechanical analysis. This is our model in MATLAB software, in OpenSim software. So why do we think there's a new tendency for this kind of parameterization? Because there's no dependency on the base model. If it's a CT scan which has anatomical particularities, MRI or kinematic analysis, everyone is different, so we cannot be dependent on the base model to get the same results. And also because if we have the same starting position, we have the same comparable results with the same conditions. And by the end, allow us to easily parameterize other shoulder joint positions. So we have a starting point which is common, but we also can change the shoulder position, the shoulder complex joint position into different positions using these parameters. So another difference of our approach is to consider the sternum as a center of rotation of movement called the fulcrum, which is not present in almost the studies that does not consider the sternum or even the clavicle. This is our references that we use to get this new approach. I'll have to the acknowledgement to the FCT, Fundação para Ciência e Tecnologia, that supported this research, and teşekkürler. Thank you.
Okay, teşekkürler means in obrigado as your language. Thank you so much. De nada.
Okay, thank you, Vitor. Okay, questions at the end. So we now have Inês Cruz. Maria Inês Cruz presents sport biomechanics work, development of a test bench for analyzing force transfer from athlete to blade. Okay, Inês.
That was
And also backgrounds are very important. So Vitor's background is very strong for this session.
I agree.
It's just to get some inspiration.
Can you hear me?
Yes.
Okay. I don't know if I have the right. It's right?
No,
No.
because you
Now we
shared
can see ourselves.
your PC, the screen, and not the PowerPoint.
Ok, vou tentar.
Inês partilhou o ecrã e não o PowerPoint. Quando carregas no partilhar, há um conjunto de opções por aí abaixo e aparece o PowerPoint. Vem por aí abaixo, por aí abaixo, por aí abaixo. Se tiver o PowerPoint aberto, ele aparece janela ou ecrã.
Sim,
Aparece janela. Já está? Ok.
Sim. Consegue ver?
Trabalho.
Dá para ver, não dá?
Dá, Inês.
Ok, eu vou pôr em modo apresentação. Ok.
Está correto agora.
Tá? Ok. Good morning, everyone. My name is Marines, that the professor will say. I'm a PhD student in mechanical engineering, and today I will try to present one part of my PhD. It's the presenting of conceptual development of a test bench that aims to estimate blade force in paddling through strain measurements on the paddle shaft. In paddling sports, propulsion depends on how effectively the athlete transmits force to the water. Traditional, this has been measured directly at the paddle blade, but blade-mounted sensors are fragile, hard to calibrate, and can affect hydrodynamics. The examples that I show you here illustrate some of this approach, including pressure sensors and fiber optic systems embedded directly in the blade structure. An alternative is to place strain gauge on the shaft, which allows for indirect force estimation. However, most studies only estimate force in one direction or at a single point. The mechanical link between what happens at the hands and what happens at the blade is not well understood. For that, the goal of this work is to understand how the force applied in the hands can propagates through the shaft and reach the blade. For this, we have developed a system with, here we have some strain gauge are placed around shaft near each hand to capture the formation. For that, we need to understand the mechanical relationship between the force applied by the athlete hands at the resulting reaction at the blade. It was necessary to develop a dedicated test bench that you see in this image, and we can keep isolating and measuring these components under controlled conditions. This is the custom test bench. We have a calibrated vertical load is applied at the top hand using a screwdriver mechanism. Não consigo dizer. The paddle is supported at the bottom hand with a bearing that allows free rotation, and the blade is mounted on a rigid aluminum-based instrument with load cells. The test bench allows us to first quantify the blade reaction force in 3 dimensions, simulate realistic paddle-water interactions, improve sensor calibration, and finally generate reliable data to train neural network models. For that, I will show you each part of the test bench. First, bottom hand. It's like a rotational stabilizer and provides passive support through a bearing that allows free rotation. This configuration reflects the role of the third finger of the lower hand,
as described in the literature, which serve as a pivot point during the stroke without transmitting significant force to the shaft. The next hand is the top hand position. Here we apply a vertical force that I said before. We're generating a moment that replicates the mechanical action of the top hand during the paddle stroke. This setup enables control simulation of the force propagates along the shaft and reach the blade. Now, the blade, we have two parts. The first part is the reaction force at the blade measured using the four load cells that are in the lateral of the base. We can capturing the lateral and forward components at the force that you can see in this figure in my left. Okay, I think I have my, okay. Next, we also measure vertical component that results from blade water interaction. The goal is to quantify this force without placing sensors directly on the blade. For that, we need to replicate realistically paddling conditions, like try to implement an interface that simulates the resistance of the water to the blade movement. This will allow us to reproduce the hydrodynamic behavior of real strokes under controlled conditions. As I said before, we want to make a neural network. For that, we have the direct model. This model, we apply a known force and measure the resulting strain at 8 points along the shaft that I show you in the third slide, I guess. This relationship helps us characterize the mechanical behavior of the system and validate the data acquisition. But we want the inverse problem. We need to estimate the force at the blade using only strain data from the shaft. We propose using a neural network that I say that receives shaft strain data as input and output as a predicted distribution of force at the blade. Try to make a mapping like we see in the last image. For our neural network model, we want to receive 8 strain inputs, process them through 2 hidden wires, and output 3 components of force vector. Before training this final model, we develop and test a preliminary network that estimates the magnitude and position of the applied force on the base, using only the reaction force measured by the load cells. The model is still under refinement, but preliminary results show promising accuracy. We have a error in force prediction of the 3%, and in position estimation, we have 2% of the error. The next step is to collect a complete data set, combining all strain gauged signals from the shaft and the blade reaction force. Now with the interface installed to simulate water resistance, and this is allow us to train and validate the final neural network model under more realistic loading conditions. This work is not just done by me. This is my supervisors that give me all the guidelines to make this project a success. And this project is sponsored by national funds. I want to thank you, and I'm grateful for your attention. If you have some questions, I can give you.
Thank you so much.
Answers.
Okay, thank you, Inês. Questions after. Thanks for presentation. And now we have João Maia, also with the sport biomechanics work in the sport domain, and his effects of game experience on decision making in basketball, a study with under 16 female players. Is that okay? João?
Hello. Good morning, everybody.
Thank you
Let
so
me
much.
try to share my presentation. Everybody is watching the right
Yes.
PowerPoint, right? Okay. So as Professor Luis was saying, my study is about the effects of the game experience on decision making in basketball, and our study was made with under 16 female players. So, beginning with a quick introduction, decision making is directly linked with a high performance in team sports. Okay, in this case, we are studying the importance of decision making in basketball, but decision making doesn't happen isolated. Okay, it's a complex process that integrates physical, technical, tactical, and cognitive skills. One of the key factors that influence the decision making is the experience, and this also plays a big role in shaping perceptual cognitive abilities in the players. So with this, we have three objectives. One, understand the impact of experience in the decision-making process. Secondly, compare individual and group decision-making, and also understand what are the key factors that athletes think are the most important for a good decision-making. And we also created two hypotheses. One, that game experience has a positive influence on the quality of the individual decision, and also that team decision making will have a higher quality than the individual ones. Our sample included 11 female players between 14 and 15 years old, and we had two teams, one with 6 years of experience and the team B with 7 years of experience. The protocol used had two phases. The first phase started with us selecting 36 videos from the Under 16 European Championship. After we validated the videos with national team coaches, and each athlete watched 3 validated videos and responded individually. These responses were scored by a 0 to 2 scale. After we grouped the players in heterogeneous groups with good decision makers and bad decision makers, and they were first evaluated by their coach if they are good or bad decision makers. And as a group, they also discussed 3 videos. Also, they identified that in their opinion, what are the key factors for a good decision making. In the group phase, in the individual phase, we didn't found statistically significant differences, but we noticed that more experience didn't always mean better decisions on court. So as we can see, we have 3 different participants with different practice times. We have 2 that are bad decision makers, but as we can see, they have a higher score than the one that is considered a good decision maker. In the terms of experience, we have 1 player that has several less hours comparing with participant 8 and participant 10, but he also scored a high value comparing to the other ones with a higher practice time. This suggests that experience alone may not be the only determining factor for a good decision making. In the group stage, in the first graphic we have the scores of the groups. All of them had higher scores comparing to the individual results. And we understood that normally in the group discussion, the player that was considered the best decision was the one taking the lead of of the talk between the players. So this means that in a group, the ones that know that they don't have the same quality in terms of decision, they let be led by the one with good decision normally on court. In terms of the factors, we can watch that there are some differences between Team A and Team B. While Team A reinforces a more tactical approach, because we can see they have higher values for watch defense, read the game, or positioning on court. Team B was more for cognitive things like confidence, like creativity, and speed of the decision. In terms of and to conclude, we need to understand that decision-making training must be integrated into the daily practices, because it's one of the most important things on basketball. It's not only score baskets. We also need to make decisions all over the game. We understand that experience alone isn't enough, and that group dynamics also play a key role for a good performance individually, but also for the team performance. And we need to understand that training quality and coaching style are also key for the development of the decision-making skill, because we had two different teams that had a different approach. So with this we understand that each coach prefers different things. For future studies, we want to expand the sample of our research. We want to create conditions that make us closer to the game itself, not only on video but in court, and create an environment when in the practice the coach can use video and discuss with the players which are the best decisions for each situation. That wraps up my presentation. Thank you very much for your attention, and I'll be happy to take any questions from you.
Thank you so much.
Okay. Thank you, João. Thank you so much for your presentation. So we finished the 5 presentations. Arif, the ball is on your side.
Okay, thank you so much.
We can now open a discussion. Also,
Okay.
if the presenters want to make some question or something that it's open to all. Okay.
Okay. First of all, I would like to thank all of works or all of students or all of PhD advisors for yours. Thank you so much. And also, is there any question for my country? Or is there any question for our university system? So we have some possibilities for foreign PhD students. So if you want to, if you will be here for 1 semester or 2 semester with Erasmus component, so we have some possibilities, and we have some things for you. And also, is there any question for me, for our university or for our Turkish educational system? For PhD? No. Thank you. I have a question for Mariana and Vitor. So it's so hard to simulate real bioparts. So you have got so stronger PC or etc. As you know, you have got to a strong solver. So it's too hard to generate real parts with finite element models. How to eliminate the problems with your models?
So if I could understand correctly your question, to simplify our models.
No, not to simplify the models. If you have not to get a strong solver, you have not to get real solutions. That's the reason you need to you have to, not must, have to get real so strong solver. That's the reason how to eliminate the problems. Maybe some points or other things. Also, meshing process is so hard to generate, as you know. That's the reason how to eliminate the problems with your models.
Yes, first of all, as a starting point, we should have correct CAD models to avoid those kind of that kind of problems. We used to have some geometries, some CAD models from the humerus and the scapula that were obtained from CT scans, and which were segmented using Slicer 3D, for example, and the geometry was not perfect. So by that we could not have real.
And also your geometry is so hard. So tibia
yes.
is similar parts, but
Yes.
scapula or other bones are very complex geometries.
And if we don't have a simplified geometry, like the digital geometry from saw bones, it's even harder to get the correct mesh model or the finite element model to make the correct approach, the correct simulation. So by that, I'm very lucky because I have access to CAD models which are perfect. Even they have the inner and outer layers like trabecular bone and cortical bones. So for me, I'm a very lucky guy which has access to very correct models. I don't know if Marianne has the same problem.
Yeah.
Or the same lucky.
In the measure of the bones, yes, we have the model by how we say
the CAD models.
The CAD models from Sorbonne. But I also have an early study when that I need to use tech models like MRI models, and I need to do several iterations to find a more perfect model. But I think that the major decision is to do several iterations and try to eliminate the gaps that are in our models. We don't have a perfect models. We try to achieve them.
Yeah.
I remember when Arif was here, 12, maybe 10, 12 years ago, you have hard work with some teeth because the final model was not perfect. So
yeah.
I can see what you are talking about.
Yeah. And also, you have got the general real model. Dynamic analysis is so hard. That's the reason, like crash analysis in Elastina and other topics also. That's the reason the start point is true and real geometries. And also after that, you get the true meshing parts. That's the reason this is the second phase of the true finite element analysis process. That's the reason geometry and meshing parts are so hard, and you get strong PCs or solver and other things. That's the reason. Yes, finite element analysis is very perfect results, but get us to very perfect results. But it's so hard to generate real models. The first base is so hard. That's the reason.
Yes.
Thank you so much.
Trying to reply the CAD model with a finite element model is very hard.
Yeah. Maybe first step is important for the finite element process. The second steps are less important than the first ones.
Yes, but also very important because we have to reply the phenomena, we have to reply the behavior, the conditions. And I believe that the secret is to simplify correctly the model. Not only the mesh model, but also the border conditions and the loading conditions. The secret to get the finite element model correctly is to simplify.
Okay. Thank you so much. And also, Çağatay, is there any question?
No, but I can say this. When you use a Solvo model, it's easier to make analysis because the model is smooth and machine quality is quite good. But if you try to create a model from MRI image using like a software like Mimic, in some point you lose lots of geometry because when you make a smoothening operations or wrap operations, you lose some details. And because of some spikes and sharp points, your mesh quality getting worse and worse, and it increased the analysis time. So using Sawbone model is really make the analysis easier for you. So
Yes, it is.
good way to start.
But there are some difficulties because we get the CAD models, but it has no references, no planes, no axes. So we have to parameterize everything to get a perfect assemble or to get perfect conditions, because the SolidWorks models do not have any axes or any planes.
Yes, correct.
So a lot of hard work to get the real axes and the real mechanical axes, anatomical axes, real hard work.
And another thing, Solvo models are already validated. But if you create your own model, you need to validate it with this, other research as well. So it's another good thing with using
Exactly.
model.
Okay.
Thank you.
Thank you so much. Maybe next time we will meet is the same place. Who knows?
Just face to face.
Face to
Okay.
face.
I
Yes,
have
wish for it.
Yeah.
okay. I have one question to João Maia concerning the work.
Basketball players.
Basketball players. And why the shows to under 16? Why not more experienced players with a feedback from backwards? And why that age?
First, because at the time I was the coach of that team. And it was easier for me to start the study there because I know the players, I know how they can, if they are good or bad decision makers. But I agree with the professor. I start the PhD project now, and the goal is to do it with the highest level players that we have in Portugal, to see if really experience matters or not, because it's a completely different level. We are talking of under 16 that plays in Coimbra, and we want to do it now with senior players that plays national team and also European competitions. But yeah, it will be probably some different results and a different way of approaching the decision-making study.
Okay, thank you so much.
No problem.
And also, I have a question to Katerina. It's also in the basketball, because Katerina, you evaluate the strength of the hand, mean all the hand. Is that?
Yeah, we have a dynamometer, and the athletes like press the dynamometer with the maximum force, and that calculate the value.
Yes. Based on your experience, do you believe that other type of measurement of forces will be important? Because I know nothing concerning basketball, but I believe that sometimes the fingers will have a strong mission in the basketball, not only the hand, strength of the hand, but also the strength in the fingers, particularly the motricity. Is that important, or what is your opinion?
I think, like in the shooting, the wrists do a better job than the fingers. The fingers don't do force like.
So the fingers are not important in the player.
No, they are, but they are more to guide the ball than to do force in the shooting.
Okay. Basketball, Arif, Shatai. Do you have questions to Catarina
Thank you
and
so much.
João?
Marina, is there any question for us?
Catarina and
No.
João. No? No questions? No curiosities? So I have one question to Inês. Maria Inês Cruz. You are developing a meteoristic techniques based on neural networks for your inverse problem. What do you have a plan if the neural networks don't fit what you want to be fitted? Means don't understand, don't estimate well the forces and the positions. What will be expected?
Now we will try to use the one neural network, but if all things don't work together, we try to make different neural network to do that. But I know that if you don't have success with this, we can try with another method. I don't remember the name, but I think we have another way to try to predict the blade force without sensors, or put some sensors in the blade, only the test bench, because we can try to have more the force localized in the blade, because the geometry of the blade is not linear. And then I think it's another way or another method, unless I think I don't know the name, but I know that you have another method that can make the same job that the neural network. You know that.
Support machine vector?
Yes, it's that.
Okay. More questions, more discussion?
I have a question for Catarina Amaro. Hello, Catarina. In your slide number 7, I had it out because it seems like opposite results, but for sure are not, that women implement much more velocity in ball than men. I believe it was a big gap between the velocity that men applies in the ball and the gap and the velocity that women applies in the ball. At first impression, it seems it's the opposite, because men are stronger than women, so they should implement much more force. I believe the reason should be control. Men control much more the gesture than the women, so women apply much more velocity. What do you think about that?
Oh, good question. Thank you so much.
Yeah, it's interesting. When I had these results, I also think this make no sense. But I think it depends on the angle of the shooting too, because the men's don't need to that much velocity because they shoot higher, so the ball goes like more directly to the basket.
Okay.
So probably they don't need to do that much velocity. But when I hand my kinematic analysis, probably I will understand this better, because at this point I only have ball values. But yeah, I don't have like a scientific answer.
But don't you think also it's about control, that men can control much more the gesture than the women? And with much more control, we apply less velocity because we have much more precision.
Yeah, and also the ends of men's are bigger, so they occupy more the ball. So
yes, much more stability and control.
Yeah, Yeah.
Okay, okay. Thank you.
Thank you.
Thank you so much. And also, thank you for all of your presentation. And also, I have a question again. Is there any question for our university or our country? Thank you.
I only make a challenge for
I know your country. That's the reason. I think that Professor Rosario and Vitor last time were here, but I think that Mariana, Katarina, Maria, Joao, maybe you haven't been here again, or is it your first time in Turkey? No, I don't know. That's the reason.
Sorry, but I've been in Turkey 10 times already.
10
Between
times?
Istanbul and Izmir. Yes.
Oh, okay.